Welcome back to our software engineering program. In today's explainer, we're going to methodically break down Section 18.3, which covers a genuinely fascinating and absolutely crucial topic, service engineering. Think about the modern digital world for a second. We literally can't run our global infrastructure without software, and increasingly, that software is built by connecting independent, reusable pieces of functionality across the internet. We call these pieces services. Today, we're going to learn exactly how software engineers design and build these services from the ground up. Here's our roadmap for this lecture. 1. Introduction to service engineering. 2. Step 1. Candidate identification. 3. The B2B catalog example. 4. Step 2. Service interface design. 5. Step 3. Implementation and deployment. And 6. Summary and exam focus. All right, let's jump straight into Section 1. Introduction to service engineering. So let's start with a really clear understanding of what service engineering actually is and why it's so foundational. To put it simply, it's the process of developing robust, reliable, and reusable services for service-oriented applications. You see, in software engineering, we really don't want to reinvent the wheel every single time we build a new app. Service engineering is all about looking closely at everyday business processes, finding the reusable abstractions, the tasks that happen over and over again, and turning them into standalone services. And crucially, these services have to be highly documented so they can be easily discovered and understood by potential external users. Taking a look at this diagram from the textbook, you can see how we actually achieve this. Service engineering follows a strict, logical, three-step process. First up, we have candidate identification, which is where we figure out what services we actually need to build. Second is service design, where we plan exactly how the service will communicate with the outside world. And finally, implementation and deployment, where we write the actual code and make it live on a server. We're going to walk through each of these three stages step by step today. Moving on to Section 2, Step 1, Candidate Identification. This first step is where developers really have to put on their analytical hats. You look closely at a business's processes to discover which reusable abstractions can be converted into useful services. To figure out what should become a service, we rely on a classic classification by an expert named Erl. According to Erl, you must recognize three fundamental types of services. The first is utility services. These implement general application-independent functionality. Think of something like a simple currency converter. The second is business services. These are tied to a specific business function, like a system for student registration at a university. And the third is coordination services, sometimes called process services. These support complex workflows that link different actors together, like an automated process for ordering and paying for goods from external suppliers. Furthermore, Erl suggests that these services are divided by their orientation. If you look at this table, it maps Erl's three types, utility, business, and coordination, against two orientations, task-oriented and entity-oriented. Notice how utility and business services can be either task or entity-oriented, but coordination services are always task-oriented because they inherently manage active workflows. Let's just make sure we clearly understand the difference between those two orientations before we move on. A task-oriented service executes a specific process or action. It actively does something like validating a claim form or converting that currency we talked about. An entity-oriented service, on the other hand, manages the state or data for a specific business resource, which we call an entity. A great example of an entity is an application form, or maybe a database of employee records. Section 3, the B2B catalog example. Okay, to ground all this abstract theory in some reality, let's step through the textbook's practical example, building a service for a business-to-business, or B2B, computer equipment catalog. Imagine a company that sells computer equipment. They have special prices agreed upon with large corporate customers. So instead of a normal consumer website, they want to build a catalog service that the external procurement systems of those large companies can talk to directly. This specific catalog service is a perfect example of an entity-oriented service. Why? Well, because the entire service revolves around one central resource, or entity, the catalog itself. When we're identifying this candidate service, we absolutely must define its functional requirements. Functional requirements are simply the specific actions the system must perform. Here we identify operations like make catalog, which creates a custom view for a specific company, or check delivery, which calculates when an item will arrive. These map directly to the daily operations the service must be able to execute for the user. But we can't stop at just what the service does. We also have to define how well it does it. And these are our non-functional requirements. Alongside the functional operations, we have to specify constraints. For example, ensuring it can handle a peak load of, say, 100 requests per second. We also need strict access restrictions to maintain system integrity and ensure confidential pricing remains completely hidden from unauthorized users. Section 4, Step 2, Service Interface Design. So, with our candidates identified and our requirements written down, we need to bridge the gap to actual code through our architectural choices. First, you define an abstract interface, basically just the logical inputs and outputs. Then you have to decide how to realize it. You could choose SOAP-based services, which are robust, a bit high-weight, and rely on standard XML messages and WSDL descriptions. Or you could choose RESTful services, which are much more lightweight and map your operations directly to standard web HTTP verbs, like post, get, put, and delete. Actually, a lot of modern cloud providers will offer both, just to give developers maximum flexibility. Okay, so before we write a single line of code, we have to talk about things going wrong. A really common misconception students have is that exception handling just fixes broken code internally. But in service engineering, why is it considered an absolute defensive necessity right from the interface design stage? The answer is trust, or rather, a complete and total lack of it. You have zero control over how external client programs interact with your service. You have to assume external users will inevitably send incorrectly formatted data, request items that don't even exist, or just completely misunderstand your documentation. Because of this, you must aggressively define exceptions in your interface to catch and manage bad external data gracefully. You want to return clear error codes instead of just letting your system crash. Taking a look at this UML, or Unified Modeling Language diagram from the textbook, you can see how it explicitly maps constraints to specific error codes. Look closely. If a user requests 0 items, that breaks a constraint. And the interface design specifically dictates a must return error code 4. This ensures the external developer knows exactly why their request failed, and more importantly, how to fix it on their end. Section 5, Step 3, Implementation and Deployment. All right, we've identified our candidate and designed an interface that anticipates errors. Now for the actual programming phase, implementation. This obviously involves writing brand new code in languages like Java or C#. But quite often in large enterprises, you aren't starting from scratch. Instead, implementation means taking old existing software, which we call legacy systems, removing their application-specific behavior, and wrapping them in standard service interfaces so they can suddenly communicate over the modern web. It's a great way to breathe new life into old systems. Once the code is written, we deploy it. But listen carefully here. Deployment isn't just about putting the executable file on a server so it runs. A service is literally useless if nobody knows how to talk to it. Deployment heavily relies on publishing detailed, trustworthy documentation. Whether that's an informal description for a REST API or a formal WSDL document for SOAP, you absolutely must give external developers the instruction manual they need to consume your service. You should also offer subscription info so they know when you update things. Finally, Section 6, Summary and Exam Focus. That covers the 3 main stages of service engineering. Let's recap with a focus summary so you know exactly what to study. If you take away anything from today's lecture, make sure you memorize Erl's classification. You need to be able to define utility, business, and coordination services, and explain the difference between task and entity-oriented services. Secondly, you must be able to articulate why exception handling is uniquely critical in service engineering. Remember, because your service operates on the open web, you can never, ever trust the data coming from external inputs. And that brings our explainer to a close. We now know how to build a single, robust service from scratch. But I want to leave you with a provocative thought as we prepare for our next lecture. Once we have all these standalone services sitting out there, how do we weave them together to build complex, cross-organizational software systems? It's like a giant puzzle. We'll be exploring exactly how to do that when we cover service composition next time. Thank you so much for joining me, and happy studying.